Thank you. Good afternoon. So this is joint work with Troels, Bjerre, Lund from Copenhagen. I'm from Aarhus myself. So the plan of this talk is I'm going to talk about just the mathematical definition of what is a proper equilibrium. I'm not going to try to motivate the concept. For this concept, we have three results, which are complexity results. So I'll describe each result and just try to give a glimpse of an idea behind each of these results. All right, so here's the formal definition of what is a proper equilibrium. So it's defined in terms of limit points of so-called epsilon proper equilibria. So an epsilon proper equilibria is something, it's a strategy profile where it's fully mixed, and then it says something about the given valuations of actions. So I should also mention that we're looking at finite games in strategic form with n players. So let's consider some player I. So he compares two actions, K and L, and if K is worse for him than L, the probability of which K is played must be by an epsilon factor smaller than what the action L is played with. So a proper equilibrium is just a limit sequence of such epsilon proper equilibria. And so if you think about it just for a little bit, you realize that if you have a strategy profile which is a proper Nash equilibrium, it is actually a Nash equilibrium. So it's okay to call it that. That's called a refinement in general. So one of the most important properties about proper equilibrium is that they actually exist. So that was shown also by Meyerson while he was introducing the concept. So the proof is really simple. It just applies the powerful Kakutani fixed point theorem. So you look at the definition of a proper equilibrium, write down the natural correspondence, and check that it has the properties needed to apply the Kakutani theorem. There's an alternative proof which appears in work by Colbert and Martin on some different topic. So what they do is that they take a game G in strategic form and generates an auxiliary game, let's call it G prime, such that if you have a Nash equilibrium in G prime, it corresponds exactly to a epsilon proper equilibrium in G. So it's actually okay to just find a Nash equilibrium in this larger game, and we know these exist also by the Kakutani fixed point theorem, or also by the Brouwer fixed point theorem. The caveat here is that we have an exponential blow up from the game G to G prime, so it's not an effective reduction as such. So of course, once you have shown existence of epsilon proper equilibria, you get existence of proper Nash equilibria just by compactness considerations. All right, so here are our three results. First result is very simple case of two players. So the bimatrix case, you're given a strategy profile, and it's even a pure Nash equilibrium strategy profile. You just want to verify if it satisfies the conditions of being a proper Nash equilibrium. That's an NP-complete problem. The two other are more about finding such a proper Nash equilibrium. The first one in general n-player games. Let's say you want to approximate such a Nash equilibrium, proper Nash equilibrium strategy profile. That turns out to be complete for the complexity class fixed P subscript A. And another result is you look at polymetrics games, you can actually get a p-pad completeness result. So all these three results are completeness results, and completeness entails both an easiness condition and a hardness condition. So how actually to think about these results? So the first one you should think of as being a negative result. So the real work is going to show into the problem being NP hard. And I think this is an undesirable property of an equilibrium refinement, that you can't even check if the conditions are satisfied. The two other results, you should think of these as being positive results. So the hardness comes immediately from the corresponding problems of just computing any Nash equilibrium, approximating any Nash equilibrium, or computing any Nash equilibrium in a polymatrix game. These two are indeed also complete for the two complexity classes. So what these show here is that sort of getting the extra properties of a proper Nash equilibrium comes for free in a complexity class sense of the word. Okay, so here's the first result I'll try to describe. So that's the verification problem, that we want to verify if a given pure Nash equilibrium in a bimatrix game is proper, so that's hard. And this was actually surprising to us. It was stated as an open problem in the literature, and other types of these results for other refinements showed that actually you could verify things in polynomial time. So this here is the first one that turns out to be hard. Maybe the problem is that you actually don't want to have a proper Nash equilibrium. If you have a so-called symbolic Nash equilibrium, and I'll describe what that is later, you can actually verify it efficiently in polynomial time. And you can also compute such a Nash equilibrium by Lemke's algorithm. So the corresponding problem would be in PPAT. So here's what a symbolic proper Nash equilibrium is. So now your probabilities of given actions are described as polynomials in a formal variable epsilon. And the property required is that for every sufficiently small but positive epsilon, the induced strategy profile must be an epsilon proper Nash equilibrium. So in particular, letting epsilon tend to 0, you retrieve the actual proper Nash equilibrium from such a symbolic representation. So what is the idea behind the proof? I also wanted to say that in 3-player games, things are completely different. Everything is hard about verification of any standard refinement. So our proof is based on the of a well-known bimatrix game by Konitzer and Sallenholm, used for showing that various decision problems regarding Nash equilibria are actually NP hard. So what they construct is that they take a 3CNF formula, or actually a CNF formula in general, and construct a symmetric bimatrix game. And what is nice about that is that we have a one-to-one correspondence between satisfying assignments to the CNF formula and Nash equilibria where both players receive payoff 1. From that, you derive the following game. So you just add another strategy. Let's call it a fail-safe strategy F. And that ensures by playing F, you get payoff guaranteed 1. And that introduces an always present Nash equilibrium inside the game. So in effect, you'll have a Nash equilibrium F, F, which always exists, and all other Nash equilibria are in one-to-one correspondence with satisfying assignments of the formula. So now you want to say something about these other Nash equilibria and use that to prove hardness by reduction from 3Z. So this here is not very useful for our purposes because think about the definition of epsilon proper equilibrium. So that's, you can think of that as being trembles. So you actually have to play a fully mixed strategy. If you do that in the Konitzer-Sallenholm game, then the only best reply for each player is F. So F, F, the Nash equilibrium that always exists, is the only proper Nash equilibrium. So we can't hope to say anything about anything interesting about proper Nash equilibrium in that game. So we'll just change it slightly. We'll change this fail-safe payoff to be just a half. And to make the analysis actually work out, we need to increase one of the penalties inside the Konitzer-Sallenholm game. What happens is that now satisfying assignments to the CNF formula indeed induce proper Nash equilibrium in the robust game. But we don't have a one-to-one correspondence between satisfying assignments and Nash equilibrium anymore. It's a one-to-many correspondence. Okay, so once you have this, we can complete the reduction by a small trick. So we're going to introduce a new strategy G, and that's going to be the a Nash equilibrium always, G comma G, and that is going to be a proper Nash equilibrium if and only if the given formula has a satisfying assignment. There are two directions to this. I'll just talk about one direction here. And the idea is you look at the definition of the proper Nash equilibrium. So assume that actually G comma G is a proper Nash equilibrium. So you have a sequence of epsilon proper equilibrium that converges to G comma G. And then you're going to condition on not playing G. So G is sort of a strategy that always gives payoff 1. So if you condition G out, you're going to get something which is also an epsilon proper equilibrium in the restricted game, so the robust Konitzer-Sandholm game. And also you're going to observe that G needs to be a best response always. So the conditional strategy profile cannot converge to F comma F. So it has to converge to some other Nash equilibrium, and that must be a proper Nash equilibrium. Or it certifies that the formula has a satisfying assignment. All right, so that's the first result. Next result is about approximating a proper Nash equilibrium.
So in the previous thing,
yes.
when you remove G and then look at the restricted strategy, then it has to converge to a Nash equilibrium.
Yes.
Or a proper Nash.
It actually has to converge to a proper Nash equilibrium.
But in the remaining game, F comma F is the proper Nash equilibrium.
It is, but you're not. So the payoffs guarantee you're not converting to F comma F. So maybe I said it too fast.
Oh.
Okay. All right. So here the task is. So you're given a strategic form game. You want to approximate a proper Nash equilibrium. So a proper Nash equilibrium can involve irrational probabilities. So you just want to compute some rational strategy profile which is very close to that actual point. And so what is fixed P? So that's maybe not the most well-known definition. So it's by Ithaca and Yanakakis, and what they did was that they tried to capture efficient proofs, existent proof by Brouwer fixed point theorem. So anything that is or can be reduced to a fixed point of algebraic circuits computing some continuous mapping from a convex set into itself. And they show that this completely characterizes computing an Nash equilibrium in 3-player games and beyond. So here our trick is that we'll not be able to compute actually or we'll not attempt to directly compute a proper Nash equilibrium or approximate it. We're going to look at an epsilon proper equilibrium, and we're even going to relax that definition. So we're going to look at something called a delta almost epsilon proper equilibrium. And it's just like an epsilon proper equilibrium, except that you only care about looking at actions that have a significant difference between their actual valuations, so by at least delta. Then you impose something about the probabilities. Then there's a strong paradigm or a powerful tool called the almost implied near paradigm of Anderson. So it just says that if you make epsilon really, really tiny, so a virtual infinitesimal, and relative to that you make delta really, really tiny, then just approximate a delta almost epsilon proper equilibrium, then that's just as good as approximating an epsilon, a proper Nash equilibrium. So the idea is the following. Now you want to make a fixed point computation. So I'm trying to describe that function. So you're given a strategy profile X, and you compute how each player evaluates each action. And now we're trying to make an operator that fixes violated constraints in the delta almost epsilon proper equilibrium definition. So that said that if two valuations are at least delta apart, it says something about the magnitude of the probabilities. So if you have two valuations, at least delta apart, you want to make the probability of the worst action at most an epsilon factor less than the other probability. So that's an operator, and we'll see that it actually works to start with the uniform strategy profile and iterate that polynomially many times and normalize. An important technical insight is that, so we're computing a continuous function. So that step of just making a conditional assignment, that's not a continuous operator. So instead, we'll simply do a linear interpolation between actually assigning it by an epsilon factor of one probability and leaving it. Okay, let me not say more about that. So just a few words about the last task. That's about computing a polymatrix proper Nash equilibrium. So the idea is that you extend a previous result by my co-author that worked for bimatrix games and put that into a LCP formulation of computing Nash equilibria in polymatrix games. So PPAT, that is the definition by Papadimitriou, and that completely characterizes computing Nash equilibria in bimatrix games and also computing Nash equilibria in polymatrix games. One technical comment I just want to highlight here is that there's a technical obstacle for showing that computing a proper Nash equilibrium is in PPAT, because verifying its conditions is NP hard, and problems in PPAT are required to be inside of TFNP, so you need to be able to verify efficiently that you have found what you're looking for. All right, so we actually compute a symbolic proper Nash equilibrium. And that's by going back to the construction of Colbert and Mertin. And that has its exponential blow-off of an oscillatory game. And we're able to avoid that exponential blow-up in the same sense as my co-author's previous work on bimatrix games by using an extended formulation of this so-called generalized permutohedron. So it's something which has exponentially many facets, but you can introduce oscillatory variables and just get down to polynomially many facets. And you take that and plug into a classic formulation of Hansen of expressing polymatrix Nash equilibrium, and you apply Lemke's algorithm to that, and the symbolic epsilon can be incorporated into that algorithm nicely. So let me wrap up the talk. So these are the results, 3 complexity results about proper Nash equilibrium. Think about the first one as being a negative result, and the other 2 about being positive results. And also another takeaway message is that a symbolic proper Nash equilibrium might be the more useful object than actually just the proper Nash equilibrium itself. Okay, thanks.